I will stop sharing now.
Shall we move on to the next
Sure.
participant?
Okay,
As Dr. My Professor Alexandre Bernardino here. So I welcome Dr. Here to give your insightful feedback on this session and give an overview of your topics of interest, especially as we plan visual attention for robots presentation. Thank you.
Okay, so good afternoon, everyone. So I'm here with some other colleagues in this room in our lab, and so you can see my face both in my window and in Linus' window, where we can see a panorama of people here in the lab. So let me first thank for Attila for the leadership and the invitation to participate in this session. It's a great pleasure, and greetings to all the audience and distinct participants, mainly there in India, which we are very pleased to collaborate. So today I'm going to talk about visual attention. So the microphone is here on the room. Is it working well? Looks good.
Yeah, slight noise at the background.
Slight noise. Okay. So maybe if you can turn off your microphone.
So now I'm using my microphone.
Yeah, this is better.
It's better. Okay, so maybe we can exchange. So I'm going now to share some slides. So let me see. But also João Luzio have prepared this presentation. So we have been working in this topic of visual attention for resource-constrained robots. So I'll talk a little bit about some parts, then I'll pass to João, which is one of our PhD students. He will explain his work. And so this is a very important topic here in the lab because it also has this component of studying from the neuroscience, from the biology, how humans perform well visual tasks with constrained resources. So our brain is very good, but limited. So we cannot process all the information at the same time. So we have to use very specialized mechanisms to select the information that is important and be able to survive in this world. So I'll start with the brief motivation for visual attention. So when humans are performing some task in the world, so they look specifically to some points in the world that are related to the task they are engaged in, and or points that are very salient, that are very distinct, and the way we scan the scene is very specific to our goals, our motivations, our drives. For instance, on inspecting a painting like the one on the right, if people just want to get an overview of the scene, they will look in some pattern. If they're willing to understand what is the relationship between the people in the scene, they will look in different patterns. If they want to recognize the people, they will also look in different patterns. So there is this top-down aspect of vision in which the motivations, the context, the environment drives our way of looking. And then when we are looking at some specific parts of the scene, that part will be processed more accurately because we are putting more computational resources, more sensory resources in that part. And so this is very important because not only the brain resources, but also robot resources can be used more efficiently, right? And so robots have to deal with dynamic worlds. They have to have very quick reaction times to unexpected events. So it's very important to learn from humans what are the visual attention mechanisms that we use, and then to deploy them in robots. So a very important aspect in human vision is that from the beginning, our sensor is non-uniform. So our eyes, they have more acuity, more resolution in the central part of the visual field. So this is called the fovea, and it extends just for 2 degrees. So we can only see with high acuity the central 2 degrees of the visual field. So when we want to get more information from other parts of the visual field, we have to move our eyes and to put the fovea on that particular region. And our eyes then are guided by these visual attention mechanisms that drive our eyes to the points that are of interest. And so in the human eye, so the distribution of the photoreceptors is similar to a log polar distribution. So it's distributed in angles and with distances to the center in a log polar way. So this is an example of actually an hardware sensor that was made many years ago to mimic this resolution. And so because of this, we can reduce the amount of information we process by a factor of the logarithm of the number of pixels. So we have a logarithmic reduction just by design on the complexity of the algorithms that we use. So this allowed us to, many years ago, when I was doing my master thesis, to achieve real-time Activision in this robot head, the Medusa. And so we have demonstrated versions behavior. So the both eyes of the cameras can center on the target that is in the center of the visual field. Then if objects are in the center of the visual field, they will also be tracked more easily and segmented more easily because there is more information there, and in the periphery things are attenuated, and we also demonstrated monocular tracking and visual stabilization behaviors. And so this happens because, okay, so in the center there are more pixels, so if the objects are centered, obviously they get advantages. But when we are exploring a scene or doing a visual search for some item, so the objects don't come centered by chance in the eye. So we have to explore the world around. And so we have to process in these foveated images, in these blurred images, what cues can attract our attention to look at those items. And so during many years, one of the dominant paradigms was that of saliency-based visual attention, in which our eyes are driven by very contrasted features in the world. And so these features are, for instance, strong edges or particular orientations, or some particular colors that indicate the presence of some important objects like people or motion. But so these are bottom-up, let's say bottom-up cues. So they come from the data itself. But so we have addressed this problem in the context of a European project in which we applied for the first time saliency-based visual cues to a humanoid robot. And so the challenges is that robots, they move their eyes, so the scene is changing all the time. So we not only need to have these saliency mechanisms, but also some visual short-term memory that collects the information that we get from sequential movements of the eyes, and this information should be put in a egocentric reference frame that is stable. so that we can collect information a long time and reason about that. And so we have demonstrated very interesting behaviors of our robot during general visual exploration. So here the robot is just looking at the scene for interesting points, for motion, for face of people, for contrasted points. And this combined also with gaze movement controllers that look very realistic, looked very impressive by the time. So this was in 2008. But if we think, well, so the robot is just looking around, so it's not doing any, let's say, semantic task. So the robot is doing interesting exploration behaviors, but it's not recognizing yet the objects, is not searching for a particular object, is not making sense of what are the people in the scene. So we needed to add semantic information to our models. And so that's one of the topics of the thesis of João Luzio, which is how to exploit the semantic information. And particularly nowadays, there is very rich semantic information in deep learning models. So all these object classifiers, image classifiers, object detectors that we have now available for free from large companies, they were trained with millions of images, millions of objects, so they collect very rich semantic information. And so we are looking at ways of exploring directly those pre-trained models and embedding them in visual attention mechanisms. So I'll stop sharing here and I'll let João present his part. So maybe I turn off my mic and you turn.
Okay, so can you hear me? Let me share my screen. Okay, perfect. So hello, everyone. I hope everyone can hear me fine. My name is João Luzio, as Professor Alexandre already said. Thank you, Professor. I'm a second-year PhD student here at VisLab, and I'm going to talk about this sub-research field of robot attention, which is human scan path prediction. And so if we want robots that better mimic human behavior, we must first understand how they perceive their environment, right? And so just to start, I don't know how many of you are actually familiar with Where's Waldo or Where's Waldo puzzles or games. But for those of you who don't know, I'm referring to a series of children books which contain these very large illustrations of very confusing, very crowded scenes that generally follow a theme. In this case is the prehistoric era. And the goal of these puzzles is to find a particular character, Waldo or Wally, depending on which country you are. And you have to spot him amongst all these distractors that you can see here. And to make things interesting, I'm going to actually ask you to try to spot him. It's not easy, but I'm going to give you a few seconds, okay? So you're probably now looking for human-like figures, wearing glasses, maybe dressing in red and white striped patterns, right? Okay, so just time's up if you haven't been able to find him yet. Very difficult. He's right there, okay? So essentially, what was happening is that your visual cognitive system was extracting these exact same features as you moved your gaze around the image, while your cortex was mapping this information or this data in order to determine regions of interest to where you should look next. And so to the generated sequence of fixation points, as you can see here in this GIF, we refer to as the generated scan path. And so to address this challenge of predicting scan paths generated by humans in any given visual stimulus, we came up with our very own biologically inspired model, SIMBA, which is short for Semantic Bayesian Attention. And this model leverages pre-trained object detectors, as Professor Alexandre was saying, in order to extract these high-level features from fields of view similar to those captured by our very own eyes, so foveal vision. And so essentially, this information is cumulatively gathered from multiple points of view. This information is fused within a probabilistic framework to generate or to build semantic maps, which are used to predict the next best fixation at each iteration. And so the scan path is generated in loop until some terminal condition. And so this framework can be applied to multiple visual tasks, such as, for instance, target present visual search, where we have a targeted object that we want to find, or even in other settings, such as target absent visual search, where you want to find an object that is not contained within the scene where you are searching in. Both settings are interesting in the sense that we are trying to understand what are the key features that really capture our attention, the ones that are related to the object that we are searching for, but also the ones that are not directly connected to it. And there are even other tasks such as visual question answering and even free viewing, which is more bottom-up saliency-based, as Professor was mentioning, and that just consists in freely exploring the environment or the scene that is given to the subject. And so, as you can see in this example, the targeted objects here are books. So notice that although the books are not initially recognizable by our model, eventually our model is able to find them after 3 or 4 iterations. And once the books are actually found, the confidence in the presence of these objects in that specific region of the field of view heavily increases. And so, in terms of results, we have by now been able to show that Semba is able to closely mimic human performance, as you can see here in this plot. Notice that it heavily depends on the size of the fovea. So if the fovea is too narrow, this limits the amount of object that can be detected in the peripheral region. So the level of blur increases, and that really limits the model and brings the performance down. So we need to have these. We need to have enough quality in the peripheral region to be able to detect these objects that aid our model in directing or redirecting the gaze to regions of interest. And beyond that, we have also been able to show that we can compete with other state-of-the-art models in human scan path prediction, although our approach is more biologically inspired. So most of the recent works in this field have been driven by these advancements in deep learning and are using not only the visual stimulus, but also the scan paths of real human subjects. And so the advantage of our model is that we are trying to focus more on the stimulus itself, extracting the semantics from the data itself, and not using information of real humans, which is closer to the way we learn. We don't know how other humans explore or search their environment. So this is something that is innate to us, that is built in our cognitive system, and that's what we are trying to use in our or apply to our model. And that's it from me. I'm passing it back to Professor Alexandre. Thank you.
Okay, so just to conclude, quickly conclude. So what I'd like to highlight today is that is this combination of foveal vision that gives by hardware severe reduction of complexity, and then the visual attention mechanisms that allow for simultaneously fast and accurate processing of systems with limited computational resources. Of course, there's no way we can process an image fully, so there will be always eventually some parts of the image that will be difficult to find or will take more time, but those parts we hope they are not important for the task. And so the other thing is, I think important is that so this semantic information that now we have in these state-of-the-art deep learning models that have been trained for many hours, many days, spending many energy and many computers. So they are available, so we should use them, not try to relearn or to retrain, because sometimes we don't have the same computational effort as big companies nowadays. So these are the main conclusions. And of course, there are many open issues that we'd like to continue working, and possibly some in collaboration with you guys. Is so first how to mix the saliency, which is a bottom-up method, with the semantic information, which is a top-down method, but the best way to mix those things. And then something that is important is that our way of exploring or our way of doing things depends on the value, on rewards that we get from the environment. So of course there are links with reinforcement learning that we want to explore in order to be more efficient in looking at scenes. Okay, so what are the features that really give value to some eye movements in visual search. So that's it. Thank you very much. And I don't know if there is time for questions. We are here to answer.
Yeah, thank you very much for this very interesting session, Dr. Alexandre and João Luzio. And yeah, it's open for questions. If you have any questions, please come forward and yeah, please.
Yes. Very good afternoon, sir. This is Jay here. I have here some few questions on this. So you're saying that there's a foveal eyes one, right? It is more onto the eyes focus point that you're focusing right now, right, sir? The
So
visual.
our eyes are have more pixels, let's say, in the center than in the periphery. But we can also think of fish eye lenses. So cameras that have a lot of radial distortion, then there is also more information in the center than in the periphery. So it also makes sense to use these methods in other types of sensors.
So you have to,
I don't know if
you're referring from only one particular point of view, right, sir? Because some is distorted and some is more onto the clear pixels are there.
Yeah. So the way we process the images, so we can either sample more pixels in the center of the image and then less pixels in the periphery. It's a kind of a compression of information. So we call this the spatial sampling mechanism. Or we can do spectral attenuation in the periphery. So we blur with filters, with low pass filters, the information in the periphery. So the images that we have shown look like this. So there is many frequencies in the center and not so much frequencies in the periphery. So they are blurred. So we have these two alternatives of representing the foveation.
So if I'm just going for an outdoor imaging, suppose if I have it more onto foggy or misty conditions, so will that be easier to identify using this approach?
So the foveation is a trade-off. So of course, if we use full resolution images, we will be more accurate also in the periphery. But then we will be spending a lot of time in the periphery, right? And so the idea is that we should sample the information from the image selectively. So there's no reason to process all the image in the same with the same resolution. But now, if we are looking for some particular object that is in the periphery, we have some information still, even if the resolution is low. And so we can use that information to guide our attention and then to put the high resolution area in that part of the visual field and then confirm if it is the object that we want or not.
Thank you so much, sir. Thank you.
Thank you. Thank you for the question.
Any other question? Yes, please, one more question.
Hi, Professor. This is Jacqueline. So I just have one question that whether
can we combine augmented reality with this visual search? If so, we can combine. What could be the impact that we can get?
Yes, that's a very interesting question. So it's a very important application of predicting the scan path of humans. And so if in virtual reality we can predict where the humans are going to look next, we can render the image in that part with more accuracy. And so in terms of computer graphics, we can be faster because we don't have to render the image with very high resolution in parts in which the human is not going to look at. So this is very much, there's a lot of interest in these technologies in predicting the scan path of humans in Meta and Oculus and all these companies that have the virtual reality goggles. So they want to be very power efficient because it's an embedded system. And so they are looking at ways in which they can save computation by using these models of how humans look at this place.
Thank you.
Thank you. Yeah, wonderful. Any further questions from the audience? Thank you very much for this great session.
Thank you.
Thank you, Alex and Joao. Okay, let's go.